is going to talk about Keplerian disks, so it's going to be interesting as well. So when you're ready, just share your screen.
Okay, you see my screen?
Yes, yes.
Okay, perfect. So I start. Hello everyone, I'm Iván Gallardo Cava from Observatorio Astronómico Nacional in Spain, and I want to thanks for organizing this event and to give me the opportunity to talk to you about Keplerian disk and outflows around binary post-AGB stars. Firstly, I want to give you a brief introduction about these objects, and that all our sources present this kind of radial velocity curve, which means that all our sources are binary. They also present a very significant near-infrared excess, which reveals that there must be a hot dust stable structure surrounding that binary system. This is the position velocity diagram of our best studied object of our sample, the red rectangle, and it reveals the beautiful butterfly shape that confirms and reveals that Keplerian rotation in the mentioned disk. And this is that we have binary post-AGB stars with remarkable near-infrared states that are surrounded by large Keplerian disks. But there is another structure that surrounds the disk. The outflows composed of gas that escapes from these wings and represents the 10% of the total molecular mass. All these sources have been very well studied in zero lines, but we find two different kinds of profiles. The first one, for example, ACR quiz, shows very narrow zero line profiles that are characteristics of a rotating disk. On the contrary, for example, RSQ, we find composite zero line profiles that includes a very narrow component, which very probably represents emission from the rotating disk. These two sources have been very well studied also in microwave interferometric maps, for example, ACR quiz. This is the velocity maps, and we also show the PV diagrams along the equatorial direction and along the axis direction. The first one reveals again that butterfly shape that shows that Keplerian dynamics that the disk of the ACR quiz has. And the PV diagram along the axis direction reveals that rhombus shape that a disk has. On the contrary, again, we have maps of RSQ, and the velocity maps reveals that the emission of this source is quite different of the one found in ACR quiz, since we find very extended nebulae compared with ACR quiz. The PV diagram along the equatorial direction reveal a very central clamp that probably represents emission from the Keplerian disk. But it is more important in this case to pay attention to the PV diagram along the axis direction, because it reveals information about the structure of the nebula. And we see that it is 40 arc seconds in size, and it contains two big cavities that also present in the, of course, in the velocity maps, and we find in another preplanetary nebula, like Javier showed us before. This is our maps, but we have to modelize to extract physical information about them. Our models consist of a rotating disk that is surrounded by an outer outflow that can present several shapes, such as an ellipsoid or an hourglass or whichever. And we have considered potential laws for the density and rotational temperature. And for the disk, we assume, of course, Keplerian rotation. And we have considered expansion velocity in the case of the outflow. And what's more important for us, for our models, is that our codes produce results that can be quantitatively compared to observation, what allow us to extract physical information about what we see in observational data. This is our model for ACR quiz. the first source that I show you in observational data. This is our synthetic PV diagrams, and I show you also the PV observational data to compare. We show that they are very similar, and I show you too the result of our model, and we see that there is a very high density region in the center, which corresponds to the disk, and a very low density region, the outflow, that surrounds that disk. So in this case, or in the case of AC earthquakes, we have a nebula that is absolutely dominated by the disk, because at least 95% of the total mass is contained here. So this source is a disk-dominated source. On the contrary, we have our synthetic PV diagrams of RSQT, and our model reveals that RSQT presents a nebula absolutely different compared to AC earthquakes with a very big, a very large extension with cavities, and a disk in the innermost region of the nebula. We are sure that part of the outflow comes directly from the disk, but we are working on what happened to the rest of the outflow. Probably it's a remnant of the previous evolutionary states of the nebula. But in the case of RSQT, 25% of the total mass is located here in a region with Keplerian dynamics. So RSQT is an outflow dominated source. Additionally, I showed you a source that would be in an intermediate state in between the disk and the outflow nebulae. It is the case of Haiti and Hercules. This is velocity maps with reduced and structured in hourglass-like form, and observational and synthetic PV diagrams along the equatorial and the axis direction. Our model reveals and confirms with observations an hourglass-like form in a very extended component that contains more or less 50% of the total mass. And in the innermost region, we see a high density region that has Keplerian dynamics, and of course it has another 50% of the total mass. So this source could be in between the disk dominated and the outflow dominated sources. This table collects our best sources in this outflow analysis, and they are sorted by the relevance of the outflow. We see that there is a group in which the disk dominated represents at least 90% of the total mass, and another group in which the disk is just 25–30% of the total mass. There is another sources that will be in between the disk and the outflow dominated, like 18 earthquakes that I mentioned before. As you can see, most of them has been very well studied with OEMA or ALMA. Now, we have studied all these sources using the 30 meters IRAM telescope to observe them at 1.3, 2, and 3 millimeters, and using the 40 meter Jeffers telescope 7 and 13 millimeters. We have realized a survey in the search of molecules. So, I present you the first molecular survey in the search of molecules in binary post-AGB stars. This table only collects detection, but we have very relevant upper limits in our submitted work. This work adds up more than 500 hours of telescope time, and it reveals, I can show you some example of our detection. For example, in the case of 59 Hercules, we have detected several carbon-bearing molecules. And in the case of RSQT, we have detected SiO, SO, and several lines of mass emission for SiO and water emission. I remember you that this source is an outflow dominated source. We can compare the emission of the most relevant sources such as SO, SiO, SIS, CS, and 8CN compared with 13CO, 12CO, and infrared emission at 12, 25, and 60 microns, and always compared with AGBs in blue for O rates and in red for carbon rates. No, doing this, we see that the emission of our objects is very low, and we can see this in our high-range logarithmic scale. But it's remarkable that that sources that in which the disk is dominated, such as AC Arculis or the red rectangle, present a lower emission.
2 minutes.
Okay, thank you. This low molecular emission is also present if we compare CO with infrared emission, again at 12, 25, and 60 microns, and always compared with AGBs. We see that the emission of CO is lower compared with AGBs, especially in the case of the disk-dominated source. It is not the same case with 13CO, where we see an overabundance of 13CO or a normal abundance of CO compared with AGBs. A relevant analysis is to compare O-bearing molecules with carbon-bearing molecules and compared with very well-studied AGBs to reveal the chemistry of our objects. Doing this, we can classify the red rectangle, RSQT, and AC Canis minoris as an O-rate chemistry. 18 Hercules, in which we have detected several carbon lines, carbon molecules, it seems to be carbon rich. And for the case of IRA 20056, we have not detected any thermal line, but we have detected SiO maser emission. And this kind of emission is exclusive of an O-rich, so we have classified it as an O-rich. And finally, this is I showed you our main conclusions of these works. So this is a class of binary post-AGB stars with near-infrared excess that are surrounded by a Keplerian disk and extended outflows composed of gas escaping from that disk wind. But there is a new kind of subclass in which that outflow dominates the nebula. The outflow dominated the nebula. They present massive outflow, and they are mainly composed of cold gas. Additionally, we present the first survey in the search of red molecules in binary post-AGB stars, and we find that the emission of these molecules is low. But this lower emission is remarkable in those disk-dominated sources. Additionally, the study to study the chemistry of these sources, we can classify it as oxygen are carbon rich thanks to our detection and our very relevant upper limits. Thank you very much, and thank you for your attention, and stay healthy, please.
Thank you very much, Iván. This is also very impressive. I mean, the huge amount of data you have and the analysis that you have already performed. So are there questions for Iván?
I have a question.
Ravendra, go ahead.
You didn't say anything about the continuum. I'm curious, do you detect the continuum in these sources as well?
Yeah, we studied the continuum, but we don't use it in our papers because it didn't reveal anything relevant about the structure.
And do you have the continuum detection at several wavelengths, or?
We have detection of continuum in several sources such as AC Arculis and RSQT, but it didn't reveal anything relevant about the structure.
No, at several wavelengths.
No.
Just one wavelength. Okay, thank you.
Thank you.
I have a question myself. So from the, I mean, you derived the dynamic mass of the central object for all the cases, and is that consistent with the envelope chemistry that you get?
In our model, with projection, we calculate velocity rotation of the disk, and with that only using equation of dynamics, we can calculate the mass of the total stellar system.
Yeah, what I'm asking is that mass, the value of that mass, consistent, assuming that that is the mass, that's the total,
Yeah.
Or the binary, yeah.
Yeah.
And for those targets, you don't know what the binary is, right?
No, but this is the mass of the post-AGB, of course, and the companion, a wave bar, a main sequence stars, or whatever.
Okay, then this is an upper limit to the mass of the AGB, of the post-AGB stuff.
Yes.
So it seems to me that those masses are very low in most cases, right? You never get anything more massive than 2 solar masses or so.
Yeah, it's surprising for us too, because I think people thought that they will find very high mass values in these objects, but our dynamic analysis reveals that they are not so high. We find low values.
And coming back to the chemistry of the envelope, I mean, for the carbon-rich targets, wouldn't you expect to have central masses a little bit higher?
Yes. In the case of 18 and Hercules, is peculiar, very peculiar, because it reveals several lines of carbon-bearing molecules, but using analysis of, for example, the NUTE of nucleosynthesis, it reveals I don't know the exact value, but it is not 100% compatible with a carbon-rich star. So this object is peculiar. In my opinion, maybe it will be some contamination in the binary system, because the mass is not compatible with a carbon-rich.
What is the proportion of carbon-rich to oxygen-rich chemistry in your sample?
We have that's all the source. That's all the source. This is our complete
So it's only one.
Yes, and that's only one carbon-rich. So yes.
Okay, I see. Okay.
And it's peculiar, very peculiar subject.
Okay, I see.
Thank you.
Thank you. Valentin, go ahead. You have your hand is raised.
Yes, well, it's a comment on the question of the mass. When these objects were detected many years ago, and I'm not sure that Iván was born at that time. At the beginning, they were assumed to be, or they were deduced to be, low mass post-AGB or post-RGB objects, because in particular of the distribution in the galaxy. So the fact that some of them are relatively low mass objects is not surprising. Which is sometimes surprising is that the central mass one finds from the rotation is even too high, higher than expected. So at present, when better distance determinations and better luminosity determinations, we don't confirm that all these objects are low mass, but I am sure that many of them really have had an initial mass of about 1 solar mass or less.
Okay. More questions for Iván? Comments? Okay, Lucero.
Thank you. Okay. It's just a simple question I posted on the chat. I am curious about these detections of maser emission. Are those new detections for these molecules, particularly in these sources?
Sorry, can you repeat the question? Are new?
If the detections of maser emission are new detections associated to these sources?
Yeah, are new detections, yes.
Okay. And the evolutionary states of these objects are post-AGB phase?
Could you repeat, please?
Sorry, it's because I don't have my headphones. But I am curious, is the evolutionary phase of these objects, because probably I got lost, is a post-AGB phase, most of them.
Yeah, all of them post-AGB.
Okay, thank you.
Thank you.
Okay, I'm also curious about the expansion velocities of the outflows that you see. What
Yes.
is the typical expansion velocity? I think it's also pretty low, but this one is like 8 kilometers per second, right?
Yes. Yeah, we find a low velocity in that outflow. In the case of Hercules, it is more in the line of the right rectangle and several objects. But in these cases of RSQT and 89 Hercules, I mentioned that part of the gas of the outflow comes directly from that this wind, and part of the outflow could be a different origin, maybe a remnant of the AGBs, but however, it presents a low velocity that confirms that it has only more or less 1,000, 2,000 years.
Okay, and have you computed already the linear momentum of the outflows in these cases? I mean,
I don't have the numbers of the linear momentum. Sorry.
Okay. Good.
Thank you.
So are there any more questions for Iván, or maybe we should just go to directly to the discussion so we can go over other talks and
Carmen,
yes.
I'm very sorry to say that, but we need at least 1 hour to make the recording of all the movies. So unless we stop now, it's going to compromise the preparation of the movie.
That's perfect. I mean, yeah. We've had a very dense discussion already, so we can just stop now and then we'll come back in an hour. Yeah.
Okay. Stop.
Thank you.
Okay.
Thank you very much.
Let's clap to everybody. Yeah.
Yes.
All the speakers.
Thank you very much. See you later.
Okay. Thank you very much, Carmen.